Hello and welcome. This is a C4, C4 video on something called related rates of change. Now, what I'm actually going to do is start off by reiterating something called the chain rule. And the reason for that is because before I start explaining what related rates of change are, we need to familiarise ourselves with the chain rule that we learned in C3. Now, the chain rule looks something like this. So, for something about dy by dx, we had dy over d of the derivative of something else, so that could be, we'll call that t, dt, times dt over dx. So the dt's would cancel out. So effectively what that is saying there is dy over dx equals dy over dx, which obviously is true. Now, in C3, the familiarity of these dt's was a bit irrelevant, because essentially what we were saying there is we weren't thinking of that equation. We just thought, well, it's the bit inside the bracket and then times the derivative inside. So the derivative of the whole thing times the derivative of inside the bracket. So we didn't really use these terminologies of dy by dt and dt by dx. We didn't really know what they meant. I mean, we did relate ourselves to the dy by dx is 1 over the dx dy, or the other way round, whichever way you wanted to think of it. So we didn't really use them terminologies very much in C3. That's what I want to highlight in this video more than anything. Okay, so hopefully I'm going to leave that up there just so you familiarise yourself with the chain rule, just in case you forget it. Now, I do have a bit of an agenda for this video, as I have done in previous ones. I've explained the chain rule. I'm going to explain now how that relates to something called related rates of change, obviously by introducing related rates of change there. One key thing to watch out for, because we put dt, I could put anything. Now, there's a strict thing you have to put for dt. You can't just put dt. You have to put whatever is related to your given question. And so it has to be either dt or it has to be d of the area. It has to be a set of something. You can't just put anything, because you wouldn't just be able to derive anything from something, because you have nothing to derive. So it's quite specific in terms of related rates of change. That's why I'm sort of expressing this video as I am. And then I will mention something that's sort of hiding from you, and then I will just use some examples that obviously I've created myself, not from exam solutions at all, and because, well, I want to go through the exam solutions the way they did it, because I think I can do a bit better. No, I know, because I was confused in the way they told me, so I'm going to try and present it in a slightly different way, which will still get the same answer, we'll still do the same questions, but you could also, if you feel like, oh, what am I talking about, you can always nip over to exam solutions, but they just complicate it more, because they were skipping steps and you weren't explaining why they were doing these steps. They just wrote it down assuming that we all knew that, which of course as a student I know we didn't. Well, unless it's just me being thick, but very unlikely, because pretty smart guy. Kidding, I'm not, average. Just try hard. Okay, so that's what the chain rule is. Now, there's something called related rates of change. Now, a related rate of change is something where we have sort of a factor to consider. Now, what I mean by a factor to consider is the best way of explaining the topic of related rates of change is through examples. So you might get one that says the length of a size increasing at a rate of 0.8 millimeters per second. At the moment, by the length of the side is 6 millimeters, find the rate of the area which is increasing. So that was an example. I'm going to go through that question in a minute, but that is the kind of question you'd get asked. Now, the rates are the differentials, and the differentials are dy by dx equals dy by dt times dt by dx, etc. So they kind of rates change differentials. So that's when you're looking at a C4 exam question, it won't say, right, okay, the next topic we're going to talk about is related rates of change, because that makes it a little bit too easy, assuming you know what related rates of changes are. So basically, it will say something where it's sort of, you think of it as a complex problem, a pub quiz problem that you might get. But obviously a bit mathematical, and your general pub user probably won't be able to do this. So kill me if you want to. So that's basically, it looks like a general knowledge question which got the word rate in there a few times. That's how to spot a related rates of change question from any other question you might get in the C4 exam. So that's one of the things to watch out for there. Okay, so now I mentioned at the start of this video, I tried to strenuously emphasise it, we don't know what DT is. But when we're looking at a question like this, we'll know exactly what DT is. We don't have to figure out what it is. Now obviously these are rates of change of something, so this is the rate of change of y with respect to t, and this is the rate of change of t with respect to x. That's essentially what it's saying. Okay, so you might get a question, something like, actually I'll use the one from that booklet here. Which one? Sorry, let me just, I'll just double check which one. Okay, so it says, is that a good example? You know what, actually, I'm going to sack this, I'm going to do, yeah, one sec, sorry. Just choosing an example to do. Right, okay, this is a good one actually. So we've got a cube here. So that's one of the key things I'd actually advise you to do. It'll be talking about a question, and the best thing to do is to draw an example of that question and what's happening, so you know what's happening. So in this question, we need to draw a cube. And obviously all the sides we assume obviously are the same, and we just put them as it being equal to x centimetres. And it said the side of a cube is increasing. The side of a cube is increasing at the rate of 5 centimetres per second. Find the rate of the increase in volume Now, one key thing here is, obviously rate means changing, which means differential. And now, when you see a question that says, this is increasing at a rate of this, but find the rate of this increasing. You've got a loads of set of rates there, you've got quite a few rates, so quite a few differentials. And the only equation, differential equation, that's got more than one differential in it is the product. There's the chain rule even, well, in that context anyway. So find the rate of the increase of volume when the length of the side is 3 centimetres. Now, we've got a rate here, we are told a rate. So the side of a cube is increasing at the rate of 5 centimetres per second. So this x is increasing at a rate of 5 centimetres per second. Now there's two variables in that one. There's the change in time, so per second. Well, there's one main, it's sort of the change in the size of it, but that's in relation with respect to the change in time. So it's 5 centimetres per second. So we've got two variables there. So it's the rate of increase of the x. So it's dx goes on top. So dx, over. Now I'm not worried about the rest of the question because 5 centimetres per second, x is increasing. So x is increasing, so that you can put that x as the displacement. So the displacement is increasing 5 centimetres per second. So second is going to go on the bottom, but obviously we can't just put the word second, we need to put time. So it's the differential of time. So it's a differential of the increase in x with respect to time. So it's dx over dt. So dx over dt, that is one of the rates. You are always given some kind of rate like that. So dx by dt equals 5 centimetres per second of increase. Now, in this, you're generally not given any lengths. Now, we are given a length here, even though it contradicts myself a little bit. When I say we're not given a length, what we mean is we are given a length here, but that's just saying find the rate of the increase when the length is this. We're not saying a length is this. We're saying find the rate of the increase when it becomes this. It's not currently 3 centimetres at the moment, so we don't know that. So we can't put x is equal to 3 centimetres. But what we do know is we do know x is equal to the length of one of the sides. So that's why we can't put x is equal to 3 centimetres. So it's essentially saying find the rate of the change of volume with respect to the time when x equals 3. That's what it's saying. So find the rate of the increase of volume. So the rate of the increase in volume is dv. And because we're given a time factor here, and there's time on the bottom here, it's going to be dv by dt equals something. Now, just as we put dy by dx equals dy over dt times dt over dx, that fact that I put dt is just a bit of a coincidence in this one. But dv by dt that's purposely there, because it says find the rate of the increase in volume. Now, the rate is a periodic change over time. Now, the rate of increase of volume is dv over dt. Now we said that dv by dt is the same as saying dy by dx. And when we said dy by dx, we put dy over dt times dt over dx. Now we're going to use the same principle, except we're going to replace y with v and t with x. Confusing that I've got t, I'm going to change this to s, so ds up here. So we're going to replace the y by v and the x by t. So that's dy over ds, that s I changed that from originally was t, but it was a bit confusing. So that's the chain rule. All this is just the chain rule at the top. And we're going to apply this chain rule to this example here, okay? So what we're doing is we said we'll replace y with v and x with t, because we said that find the rate of the increase of volume, so that's the rate of increase of volume, so it's dv over dt. And we're given a rate where we're told the side of the cube is increasing at a rate of 5 centimetres per second. So an x, we called x as one of the sides. So dx by dt is 5 centimetres per second, because that's a differential, a rate. That is why we're using that equation there. And we just simply substitute this into this formula here. So these two are exactly the same. And we're just going to, this here is that up there. So we're inputting this into that and that into that. Okay, so we're just sort of subbing these two in across, sort of like that. So we follow this pattern. What we did is with dv, the dy is on the top, so that's dv over something. And because we've got the x here, it's dv over dx, because that's the x displacement, times dx over dt, because the dx's will cancel out and we're left with dv over dt, which is equal to dv over dt, which we should know. Now, we already told dx by dt, so we can sub that in already. So dv by dt equals dv by dx. Now we know dx by dt, because we're told it in the start of the question. As we said, the size of the cube increasing at a rate of 5 centimetres per second. Now that is equal, we said that is a rate, so the side of the cube is increasing at a rate of 5 centimetres per second. Now we said the size of the cube, can't even speak anymore, I get too excited. The side of the cube is increasing at a rate of 5 centimetres per second. Now we said one of the sides was equal to, the sides are equal to x centimetres. and the size of a cube is increasing at the rate of 5 centimetres per second. So that's t. And we know x, we know dx by dt, so we sub it in over here. So that's times 5 centimetres per second. The only thing we don't know is this dv by dt. Now what does dv by dt actually mean? Well, dv by dt actually means differential of the volume with respect to x. Now, we don't know the volume. We could work it out, but we don't know these x's. But we're going to put the volume formula in anyway. So the volume is the length times the width times the height. And as they're all the same, because this is a cube, the volume equals x times x times x, which of course is x cubed. Does that make sense so far? Now, because this is dv by dx, we're differentiating v with respect to x. Now this is already in x, and we've only got one formula. So we just simply differentiate x cubed. Sometimes it's not always that easy when you get the volume formula, and we have to do something a little bit differently, which we do when we do a cone, which I'll explain in a minute. So dv by dx is equal to this derivative of x cubed, which is 3x squared, because we're differentiating with respect to x, times our original 5 centimetres squared, which is 5 centimetres per second, and that gets us 15x squared. Okay? Sorry. It's 3x squared times 5 centimetres per second, but when you put something in there, that's the same as saying 3 times 5 times x squared. That's the same as what it is already saying, just rearranged it. Okay? So it says, find when the length, so that we've done the first bit, we've done the second bit, now we're on to the third bit. When the length is 3 centimetres. Now we said x is the length of one of the sides. So we simply sub x is equal to 3 into this equation. So 3 times 3 squared times 5, that's the same as 9 times 5, which is of course, 3 times 9 times 5, almost got that wrong then, which is 135 centimetres per second, which is the rate of the change of volume, centimetres cubed per second, sorry, which is the rate of the increase of volume. Because we're talking about increase in volume, we're in centimetres cubed, not squared. That's where I made a bit of an error, and that's why we have got that. So that's basically it for any related rates of change question that you could get. Now the only difference is, for any of the questions you could get asked in relation to a cone, for example, and you would just use your formula for volume of a cone but input it in exactly the same way. Sometimes you may not be able to work out dv by dx such as that. You may be able to work out dx by dv. Obviously, it wouldn't be a dx by dv, but for something else, you just do the special case of 1 over that dv by dx, for example, to get dx by dv, or the other way round. So that's a bit of a background to the additional part of this. The rest of it is exactly the same as what we've just done on the board there. Now, sorry if I got a bit too into that. It is quite, took me quite a while to get my head around, and I've tried to explain it by keeping your mind going, what the heck is he doing? With his hands, but hopefully, maybe I'll take it too far, but hopefully you've got the idea from that. As I said, hopefully that's not too much information for you to take in. It was a little bit more difficult than that when I first looked at it. Now that's the basis covered. I was going to stop there actually, but I think I'll continue. So, as I said, I'll just give you a minute if you're going to copy that down, and then I'm going to go through a few examples that I've come up with, obviously from exam solutions, and I'll try and explain it in a different way than what they did. So I'll just give you a minute to copy that down now, and we'll get started with the rest of it in a minute. I'll just wipe this off the board. Right, welcome back. This is the what I've done is I just went away and had a quick look at one of the questions, that I was going to pick out, because that question we did just then, that was sort of an introductory question to get you used to the idea of what sort of topics, what questions you might be asked. Now, I'm going to take it a stage further. This is the limit of what they could ask you, essentially. Okay, so, should we go to that? Now, this question involves a cone, so the only slight difference is you need to know your different equations for volumes. I think we're given this in the booklet, but anyway. The question says, there is a cone of height 10 centimetres, I'm just going to put it in note form, and base radius of 3 centimetres. Is losing sand at a rate of 0.5 centimetre cubed per second, and find the rate of rate at which the depth is decreasing when the depth equals 2 centimetres. Okay, so the first thing we're going to draw, this is an upside down cone by the way, first thing we're going to draw is the diagram. So what we've got here is we've got a cone. Mine's not a very good drawing. The height is 10 centimetres of the whole cone, as we are told. The base radius, which is sort of, because it's upside down, is 3 centimetres. And we assume it's going to be sort of, we assume something like quarter full. And this is R there, and then this is H. So this coloured in bit here, that is where the sand is. And the sand is sprouting out at the end of this pointy bit. Yep, pointy bit. It's got radius and a height there, and it's losing it at the rate of 0.5 centimetres cubed per second. Now, just as before, I said what they'll give you when we relate to the chain rule of dy by dx equals dy over dt times dt over dx. They'll give you the rate of something. Now, they haven't given us the rate, saying it's losing sand at a rate of 0.5 centimetres cubed per second. Keyword there being losing. Because it's reducing, so that says at a rate, so it's losing volume essentially is what it's trying to say, and that's time, so it's volume. The dv over dt equals 0.5 centimetre cubed per second, because centimetre cubed is a measurement of volume and second is time, so dv by dt equals 0.5 centimetre cubed per second, and we can use this part to represent our chain rule. The unknown in the chain rule is going to be dv, because we are told find the rate, so again differential, at which the depth is decreasing when the depth equals 2 centimetres. So we're going to find some kind of rate, so time. So time is going to be on the bottom, and on the top find the rate at which the depth is decreasing. Now this height is the depth, so the depth is the height, so it's going to be dh by dt is going to equal, now this is part of the equation, so the dv being the unknown, that's going to be dh by dv times dv by dt, so the dt's will the dv's will be cancelled, and it will be dh over dv equals dh over dv equals dh over dv, which you should know. Now, okay, so what we've got here, put into our equation what we already know. So dh we don't know, dt, that's what we're trying to find out then too, equals dh over dv, which we don't know, times 0.5 centimetre cubed per second. Now dH over dV, we can't work that out because we can't work out the differential of h with respect to the volume. Now we can do that the other way around because we can work out the volume. Now you should know the volume of the cone is a third pi r squared times h. Okay. Now the reason we can't do dV by dH is because if we try to differentiate volume with respect to h, we've got an r squared in there, so we have to make the r squared equal. We have to change the r squared into a h. Now the way of doing that is by using similar shapes. Now again, it's a GCSE thing. What we've got is we've got a small cone here and a big cone. So this r here over h will be equal to the r of the big radius over the h of the big height. So r over h is equal to 3 over 10. So this 3 comes from here, the 10 comes from here, because they are in the same proportions, so they are similar shapes. So that's why we can work out what r is. We times both sides by h because we want to make r equal to h, to some form of h. So if we times both sides by h, that means r is equal to 3/10, or 0.3 times h. And then we substitute this formula back into there. Okay, now the reason we wanted to do that was because when we did this equation here, dH by dt equals dH by dV times 0.5 centimetre cubed, we can't do dH by dV, we can sort of do dV by dH, but to do dV by dH we need to get one factor in the volume, and we've got two. We've got the radius and the height, so we need to change the radius into some kind of height. And the reason we do that is we use our knowledge of similar shapes which have the same proportions. So if you divide the height, so radius by the height of one, you divide the radius of the height by this other one. If they are similar shapes, they will give you the same answer because they've increased in the same proportion. So that's why we've got a rearrangement for r as 3/10 times h. We sub this value back into our equation for the volume, and I've worked the answer out in here. And if you sub that in, that gets you the volume is equal. I just put v is equal to 3 pi h cubed over 100. Okay, and obviously what we need to work out now is dV by dH, because we're doing the differential of this with respect to the height, and if we did that, what we get is 9 pi. So dV by dH is equal to 3 pi times 3, reduce that by 2, so it's 9 pi h squared over 100, so you can't do anything with the 100, and because we know 1 over dH by dV is equal to dH by dV. Basically, if you do 1 over that, you flip the fraction, so a reciprocal there, so move this stupid pointless thing out of the way. So 100 over 9 pi times the height squared is equal to 1 over dV by dH, which is equal to dH by dV, which is what we wanted. And then simply we sub this into the equation there, and we get the finished formula of dH by dV is equal to our newfound 100 over 9 pi h squared times the rate which we're given of 0.5 centimetre cubed per second, and if you work that out you should get it's plus, there's a reduction of 25 over 18 pi centimetre cubed per second. Okay, so it's quite a difficult question that. So I'll just go over, so I'll just move out of the way and give you a chance to note that down. I have sort of done it in a bit of a roundabout way, but I'll just give you a minute, just copy that down, then I'm going to go through again how we did it. Oh, my voice is hurting now. So basically what it said was losing there's a cone which is a height of 10 centimetres, base radius of 3 centimetres, and it's losing sand at a rate of 0.5 centimetre cube per second. Now whenever it says something is at a rate of this, it's a differential, and because it's saying it's losing sand at a rate of 0.5 centimetre cube per second, centimetre cube is a measurement of volume, so it's going to be dV by, and because it's in centimetres per second, centimetre cube per second, sorry, it's going to have a time element as well, so it's going to be dV by dt. It's asking us to find the rate at which the depth is decreasing when the depth is 2 centimetres. Now the depth is also equal to the height, and because we are finding the rate, this is dh over dt, and because we've already got one of the differentials, which is dv over dt, we know the dh over dt is going to be equal to dh times the unknown, which is going to be dv by dv over dt, and we already know what dv over dt is because we're told it in pretty much the first sentence of the equation, which is 0.5 centimetre cubed per second. So hopefully that sort of explained where we got that from, and then we simplified it, put the volume in, used similar shapes to work out what because when we did, we can't do dh by dv, but we can do dv by dh, but to do dv by dh we needed to just have one factor in there, and we had two original factors in there. We had r and h, and because of similar shapes we can work out a formula that puts r is equal to some form of h, and then substitute that r is equal to 3/10 of h into the volume formula. Then we are just left with one factor in there of height, and then we simply just did the differential of that. And because that was dv by dh, not dh by dv, if we did 1 over dv by dh, we'd get dh by dv. And we put that into the original equation, which we already knew was times by 0.5 centimetre cubed per second. Put that in there, and that got us a final answer of the rate of 25 pi over 18 centimetre cubed per second. So hopefully that's made some kind of sense. If it doesn't, and I've just spoke a load of old tosh, then please do let me know, because it took me a while to try and figure it out, and the exam solutions guy wasn't half as sort of bold as I was there. But if you'd rather listen to someone a bit more relaxed telling you about it, then go over to Exam Solutions. It is a good website. But hopefully you can like and subscribe and whatnot. Try to get me Aston Martin. But we'll see you in the next video.